This is a video on 2.6b, and I'm going to go over numbers, let's see, 9. So let's turn to 9 first. The first thing I notice here is I've got an inequality, and I happen to also have within that inequality an absolute value. And because the inequality involves a denominator that has a variable in it, I can't just multiply both sides by x plus 1 and clear the denominator. I don't know the sign of x plus 1. If it were negative, I'd flip the inequality sign. If it's positive, I wouldn't do anything. So the strategy here, particularly when you've got an absolute value in play, because that complicates things, is to bring everything to one side and make a common denominator. So that's what I'm going to do. I'm going to bring over the 2 on the right. So let me just write what already is on the left. I bring over that 2, so then the right side now is 0. The common denominator will be the only denominator out there, which is the x plus 1. So to get that common denominator, I'm multiplying 2 by x plus 1 over x plus 1. So putting that together under the denominator of x plus 1, I'm going to get minus 2 times the x plus 1. And it's all over this denominator of x plus 1. And then let's just distribute this -2 here and combine like terms in the numerator. And that will get me, so I've got this 3 absolute value of x plus 2 minus 2x minus 4 over x plus 1 greater than or equal to 0. Okay, so now I'm ready to write this without an absolute value. And to do that, I need to see where the absolute value is changing sign. It's changing sign at -2. So let's do the first case. If I put in values into x in the absolute value x plus 2 that are less than -2, that's going to make x plus 2 negative. So I'm going to multiply inside there by -1. Okay, and now distributing the 3, combining like terms, I'm going to end up with -5x minus 10 over x plus 1. Okay, and now I'm just going to do sign analysis to solve this inequality, and then we'll talk about where the restriction comes into play. So let's do this sign analysis. The numerator equals 0 at -2, and I'm going to fill that circle in since my inequality includes equality. But I'm not going to fill in -1 where the denominator is 0 because we can't divide by 0. And if I put in a value to the right of -1 like 0, I'm going to get negative, and then I'll get positive, negative. So just solving this inequality, I'd have -2 to -1. That's where it's greater than or equal to 0. However, we've got to go back and realize that, wait a second, we put a restriction on this inequality even just to write it without an absolute value. And I put in the restriction that x has to be less than -2. Well, unfortunately, nothing in my solution is less than -2. So there is no overlap here or no solution from this piece. All right, now we're going to go to the second case. If x is greater than or equal to -2, then x plus 2 will be 0 or positive. So the absolute value isn't doing anything. So I've got 3x plus 2 minus 2x minus 4 over x plus 1 greater than or equal to 0. Okay, distributing and combining like terms, I've got x plus 2 over x plus 1 greater than or equal to 0, -2, -1, and then I'm going to fill in a circle at -2, and then I'm going to do an open circle at -1, and if I put in something like 0, I'm positive, then I'll be negative, positive. So again, just like before, looking to solve my inequality, just this piece here, looking to solve this, I would say, all right, it's positive, -infinity to -2 inclusive, union -1 to infinity. But let's remember what values of x we were putting in. We were putting in x greater than or equal to -2. So the only solutions that are the overlap of these two would be -2 and -1 to infinity. That meets the condition of greater than or equal to -2. So my solution would be -2 union -1 to infinity. Okay, so that was 9. Let's now look. Then I'm going to do 13 and the last one for at 13, which is another inequality with variables in a denominator. Luckily this time, no absolute values. Again, I cannot clear denominators and just multiply both sides by x minus 3 and 2x plus 1. Instead, I have to bring everything to one side. And I'm going to make a single fraction, which is just going to be the denominators multiplied together. So that means I've got to multiply 3 by 2x plus 1, and I've got to multiply the minus 1 by x minus 3. And now let's just distribute and combine like terms in the numerator. So then I can, once I do that, I can do my sign analysis. So I've got, in the numerator, it looks like I've got 5x plus 6. And in the denominator, I have x minus 3, 2x plus 1. And we're going to say greater than or equal to 0. And now I can just put where the numerator and denominator is 0 on my sign chart. So the numerator is 0 at -6/5. Fill that in since equality is included. Then I've got -1/2, open circle, and 3, open circle. And putting in something, I always start with the big above 3. If I put something like 4 in, everything's positive. And it should change sign everywhere here. Everything's multiplicity or raised to an odd power, multiplicity 1. So my solution, I'm looking for a positive, so I'm going to, or equal to 0, -6/5, -1/2, union 3 to infinity. That will be my solution there. All right, now it's time for this. Whoops, didn't mean to do that. This problem here. So I'm going to tell you kind of what I think is the best way to approach this, and what, for me, I find reduces any potentially careless errors and just keeps it nice and organized. So I always, when I see that there's some absolute values within an absolute value, as there is in this case, I always deal with the inner absolute value first and any standalone absolute value. So I notice in this case, the absolute value that's inside is x minus 2, so it changes sign at 2. And I also notice there's a standalone, which is 2x plus 7, and that changes sign at -7/2. So basically, I take care of these absolute values first and come up with my pieces of the function, realizing that I'm still going to have an absolute value here, but I'll do that in stage 2. So I'm going to do this piecewise function without absolute values in 2 different stages. So let's do stage 1 first here. So we're going to start with if x is less than -7/2, then I'm going to have y equals -2x minus 7 plus x. X isn't inside an absolute value, so it's never going to change here. Plus, well, I'm not taking care of this outer absolute value, so that's staying right now. If I'm putting in values less than -7/2, x minus 2 is negative, so I'm going to have -x plus 2 plus 3x and the end of that absolute value. So cleaning this up here, this first piece, this means I have -x minus 7 plus, inside I'll have 2x plus 2. Inside that absolute value, that is. Okay, so that's piece 1 of the first stage of my piecewise function. Okay, if x is greater than or equal to -7/2 and less than 2, Then now this 2x plus 7 is positive, so I'm just going to say 2x plus 7 plus x plus absolute value. X minus 2 is still negative, so negative x plus 2 plus 3x. So this now becomes 3x plus 7 plus the absolute value of 2x plus 2. All right, one more. If x is greater than or equal to 2, still have now 2x plus 7 plus x plus, well, x minus 2 is now positive, so it's going to stay as x minus 2, and now I have plus 3x. So this will be 3x plus 7 plus the absolute value of 4x minus 2. Okay, so my first stage for my piecewise function, let me write it out just so we can see it, is negative x minus 7 plus the absolute value of 2x plus 2. And this is for x less than negative 7 halves. The second piece is 3x plus 7 plus absolute value of 2x plus 2 for x between negative 7 halves and 2. And then for x greater than or equal to 2, I've got 3x plus 7 plus the absolute value of 4x minus 2. All right, so now I have to get rid of this final absolute value. So I notice in my first piece, the absolute value of 2x plus 2 changes sign at x equals negative 1. Well, the interesting thing here is that piece is defined for all values less than negative 7 halves or less than negative 3 halves. So if I'm already only putting in values for x that are less than negative 3 halves, or 7 halves rather, I know that 2x plus 2 is always going to be negative. So that piece is always going to then be negative x, let me write it down here. It's always going to be negative x minus 7 minus 2x minus 2. Again, because I'm putting in values always less than negative 3.5, so that's always going to make 2x plus 2 negative. So I can now write that piece definitively as negative 3x minus 9 for x less than negative 7 halves. All right, let's test the second one. The second one, again, is changing signs at x equals negative 1. But notice here, negative 1 is in the middle of this restriction. So it is going to take on, so 2x plus 2 is going to have, it's going to have times where it's positive, but it's also going to have times where it's negative. So I do have to break that up into two separate cases. So let's do that. The first case would be if x is greater than or equal to negative 7 halves, but less than this negative 1. So that means 2x plus 2 would be negative. So if that's the case, in other words, if I had negative 2x minus 2, then my function's going to end up being 3x, sorry, not 3x, because 3x minus 2x. It'll be x plus 5. Whereas when I'm between negative 1 and 2, not equals, and 2, 2x plus 2 just stays 2x plus 2 because the values I put in for x would make that positive. So I'll have 5x plus 9. So that was the case where, yeah, unfortunately, because of what I had inside the absolute value, it had to be broken up into two separate cases. Let's look at the last one now. This last one here is changing signs at a half, but notice the condition is I'm always putting in values greater than or equal to 2. That means 4x minus 2 is always positive. So luckily, like the first case, I'm only going to have one situation here. It's always going to be positive, so it's going to be 7x plus 5. So that is your piecewise function. So again, I think it's most helpful just to do that in two stages. Always do the inner absolute value or values if there's more than one, and any that are standalone. Do that in the first swoop, and then you'll be able to deal with what's left in the second stage. All right, well, sketching a graph, those people seem to still kind of be a little shaky on that. So It's worth trying this here. All right. And really to find the domain and range, you're going to want to have you need to kind of have an idea of what this graph is going to look like to get that accurately. So always start regardless by putting in the restriction. So negative 3x minus 9, I'm going to put in negative 7/2, which is negative 3.5. And let's see, negative 3 times negative 7/2 minus 9. Well, this is be 21 halves, or 10.5 minus 9. So 10.5 minus 9 is going to be 1.5, or 3 halves. Okay, so negative 7/2 will result in a y value of 3 halves, or 1.5. And let's plug in one more value. If I plugged in something like negative 4, I will get 12 minus 9. Let's go back here. And so it's going to look something like this. And now let's, so that's piece 1. Oh, and it would be, it's supposed to be open circle, but if we've done this correctly, it will be filled in this open circle. And indeed, when I go to the second piece and plug in negative 7/2, negative 7/2 plus 5, well, that's going to be negative 3.5 plus 5, which is 1.5, or 3 halves. So yes, it gets filled in. And then let's plug in negative 1. The output of negative 1 is 4. Okay. So that's, so I should write, this is negative 7/2, 3 halves, this first point. This here was negative 1. It should be open circle, but it'll get filled in. Negative 1, 4. And now we're on to the third piece. When I plug in negative 1, I'll get 5 times negative 1 plus 9. Indeed, it's 4. Now let's plug in 2. I'll get 10 plus 9, or 19. So we go kind of way up here. So this would be 219. And then the last thing, and it would be open circle, but hopefully when I plug in 2 into 7x plus 5, I also get 19, so that gets filled in. And then you could do one more point. If I plug in something like 3, I'm going to get 26, and the slope should be even steeper here. So that's the general shape of this graph, or this sketch. And the domain here would be everything. And the range is going to be 3 halves bracket to infinity. Okay, and that's it.